Wormholes, they're the stuff of science fiction. But what if they're more than just a plot device? Wormholes, the cosmic shortcuts that have captured the imagination of countless storytellers, might not be confined to the realm of fiction. They've become a tantalizing possibility in the real world, a prospect that keeps physicists up at night and fuels endless scientific debates. In its simplest form, a wormhole is a theoretical bridge or tunnel, a shortcut through spacetime, connecting two distant points in the universe. These fascinating structures are born from the fertile ground of Einstein's general theory of relativity, which describes gravity as the curvature of spacetime by mass and energy. Wormholes are potential solutions to Einstein's field equations, mathematical constructs that could exist within the fabric of the universe itself. The concept of wormholes isn't a recent one. It stretches back to the early 20th century, when our understanding of the universe was radically transformed by the revolutionary ideas of Einstein. It was he who first proposed the existence of bridges in space-time, a concept later expanded upon by his collaborator Einstein-Rosen. In the mid-20th century, physicist John Wheeler breathed new life into the idea of wormholes. He coined the term wormhole itself, drawing an analogy between these theoretical tunnels in space-time and an actual worm burrowing through an apple, creating a shortcut from one side to the other. However, it's crucial to underscore that wormholes remain firmly in the realm of the theoretical. They are as elusive as they are fascinating, a concept more at home in the pages of a science fiction novel than a physics textbook. But that's what makes them so compelling. They represent a frontier of our understanding, a tantalizing glimpse of what might be possible if we push the boundaries of our knowledge. They're a symbol of the uncharted territories that still await us, the cosmic mysteries yet to be unraveled. So wormholes are not merely a figment of our imagination, but a possible reality hinted at by our understanding of the universe. Let's delve into the mathematical basis of wormholes as solutions to the Einstein field equations. At its core, the concept of a wormhole is rooted in the theory of general relativity. Einstein's field equations, which describe the fundamental interaction of gravitation as a result of space-time being curved by matter and energy, allow for the existence of wormholes as a viable solution. The Schwarzschild solution, one of the simplest and most well-known solutions to the field equations, describes a spherically symmetric, non-rotating, uncharged mass. This solution gives rise to the concept of a Schwarzschild wormhole. However, these wormholes would be incredibly unstable, collapsing so quickly that not even light could traverse them. In the 1980s, physicists Michael Morris and Kip Thorne proposed a type of wormhole that could be held open by a form of exotic matter. This matter would need to have negative energy density and pressure, a concept that, while theoretically possible, challenges our current understanding of energy conditions in general relativity. These energy conditions are essentially rules about how energy and matter should behave, derived from observations of the universe. The exotic matter required to stabilize a Morris-Thorne wormhole seemingly violates these conditions, leading to significant theoretical challenges. Yet it's worth noting that there are instances in quantum field theory where these conditions appear to be violated, like in the case of the Casimir effect. While the Morris-Thorne wormhole is the most discussed model, it's not the only theoretical framework that predicts the existence of wormholes. String theory, a theoretical framework where the point-like particles are replaced by one-dimensional strings, also allows for the existence of wormholes. In this theory, wormholes are formed by strings stretching and connecting two points in space-time. Similarly, modified gravity models, which seek to reconcile the inconsistencies between general relativity and quantum mechanics, also predict the existence of wormholes. In these models, additional dimensions or changes to the fundamental laws of gravity allow for stable, traversable wormholes without the need for exotic matter. These theories provide a mathematical basis for wormholes, but their physical reality remains an open question. The existence of wormholes would have profound implications for our understanding of the universe, but as of now, they remain firmly in the realm of theoretical physics. Nevertheless, The mathematical elegance and the tantalizing possibilities they present continue to fuel our curiosity and drive our exploration of the cosmos. How do we go from theory to observation? How might we detect a wormhole? As we've journeyed through the theoretical landscape of wormholes, it's time to ask ourselves, how might we actually find one? The first method scientists propose is gravitational microlensing. In the grand tapestry of the cosmos, light doesn't always travel in straight lines. Massive objects like stars and galaxies warp the fabric of spacetime, bending the path of light that passes nearby. This effect, first predicted by Einstein, is known as gravitational lensing. Now imagine a wormhole lurking in the interstellar void. If a distant star were to align perfectly behind it, the wormhole's gravity would bend the star's light, creating a distinctive brightening event. This is gravitational microlensing. The catch? The signature of a wormhole microlensing event could be subtly different from that of a normal star or planet. Distinguishing these minute differences is an ongoing challenge for astronomers, and it's further complicated by the fact that these events are transient, lasting only days or weeks. Next, let's talk about exotic matter. Remember, Morris-Thorne proposed that wormholes could be stabilized by a type of matter with negative energy density, dubbed exotic matter. If such matter exists and is associated with wormholes, it might leave some detectable signatures. Scientists are thus on the lookout for these exotic signatures, studying phenomena such as quantum fluctuations in the vacuum of space, where particles and antiparticles pop in and out of existence. However, despite these efforts, we've yet to find any conclusive evidence of exotic matter. Looking ahead, there are exciting prospects on the horizon that could enhance our ability to detect wormholes. For instance, next-generation gravitational wave detectors. Gravitational waves, ripples in the fabric of spacetime caused by the acceleration of massive objects, were first detected in 2015. If wormholes exist, they could also produce distinctive gravitational wave signatures. Future detectors with improved sensitivity and range might be able to pick up these elusive signals. In the grand scheme of things, the hunt for wormholes is still in its infancy. The challenges are immense and the journey is fraught with uncertainty. But that's the beauty of science. It's a ceaseless quest for understanding, a relentless pursuit of knowledge. And who knows, maybe one day we'll stumble upon a wormhole, a cosmic shortcut through space and time, forever transforming our understanding of the universe. The search is on, but conclusive evidence for wormholes remains elusive. Wormholes are not without their critics. Let's examine some of the key challenges and criticisms. Firstly, we have the inherent instability of traversable wormholes. Theoretical models tell us that wormholes are prone to a kind of quantum collapse, triggered by any particle that attempts to traverse them. This is akin to trying to thread a needle with a string that causes the needle to disintegrate upon contact. Even if we hypothesize the existence of exotic matter, a form of matter with negative energy density, to stabilize these wormholes, we run into other problems. The energy conditions that this exotic matter would have to violate are fundamental to the way we understand physics. It's not just a question of finding this exotic matter, but of rewriting our understanding of the cosmos. Next, we face the open question of how wormholes interact with a unified theory of gravity. Einstein's general relativity, which predicts the existence of wormholes, is a classical theory. It does not take into account the quantum nature of reality that becomes important at very small scales. A complete theory of quantum gravity, which can describe the behavior of the universe at both large and small scales, has eluded scientists for a century. And without it, we cannot fully understand what a wormhole is or how it behaves. Also, wormholes bring with them the specter of causality violation. In simple terms, if you can travel through a wormhole, you might be able to travel faster than light or even back in time. This would allow for the possibility of time paradoxes, where cause and effect could be reversed. While some physicists have proposed that quantum effects could prevent such violations, this remains a contentious issue. Lastly, there's the challenge of energy conservation. Wormholes could allow for what's known as free energy, essentially a cosmic-scale perpetual motion machine. Energy could be dropped into one mouth of a wormhole, speed up as it falls, and then be extracted with more energy at the other end. This would violate one of the most fundamental principles of physics, the conservation of energy. However, some scientists argue that if wormholes exist within a larger multiverse, energy conservation could still hold on the scale of the entire multiverse, even if it's violated within individual universes. These challenges remind us that wormhole theory is far from complete, but that doesn't mean it's not worth pursuing. What lies beyond our current understanding? Let's consider wormholes in higher dimensions and their potential connections to other exotic phenomena. As we venture beyond Einstein's realm, we step into a universe of higher dimensions. Here, wormholes could exist not just in our familiar 3 spatial dimensions, but in spaces of 4, 5, or even more dimensions. These higher dimensional wormholes, while still speculative, could offer new solutions to some of the thorniest problems in physics, such as the unification of gravity with quantum mechanics. But wormholes are not the only exotic phenomena that could exist in these higher dimensional spaces. Cosmic strings, for example, are hypothetical one-dimensional defects in the fabric of spacetime, predicted by some theories of particle physics. These cosmic strings could have profound effects on the structure of the universe, and intriguingly, they could also interact with wormholes. In fact, some researchers have proposed the existence of vast networks of traversable wormholes linked together like a cosmic subway system. These wormhole networks, if they exist, could offer a shortcut to distant parts of the universe and perhaps even to other universes entirely. But these ideas don't just challenge our understanding of physics, they also raise profound philosophical questions. If wormholes and cosmic strings could enable time travel, for instance, how would we resolve the paradoxes that could arise? And if wormholes could connect us to other universes, what does that mean for our place in the cosmos? These questions take us beyond the realm of pure science into the world of philosophy and metaphysics. They force us to reconsider our most basic assumptions about reality, challenging us to expand our horizons and to think in entirely new ways. In the end, the study of wormholes and other exotic phenomena is not just about understanding the universe. It's also about understanding ourselves and our place in the cosmos. These ideas take us beyond Einstein, into uncharted territory. Where do we go from here? What does the future hold for wormhole research? As we stand at the precipice of the unknown, we can't help but marvel at the journey so far. The theoretical aspects of wormholes, from their mathematical underpinnings in general relativity to their potential stabilization using exotic matter, have provided us with a tantalizing glimpse into the fabric of the cosmos. The observational prospects, while still in their infancy, hold promise. Gravitational microlensing events and the search for signatures of exotic matter are just the beginning. However, this path is not without its thorns. The critical challenges that wormhole research faces are significant. The inherent instability of traversable wormholes, the open question of their compatibility with quantum gravity, and the potential violation of physical laws like causality or energy conservation are all hurdles that need to be surmounted. But let's not forget, science thrives on challenges. They push us to innovate, to think outside the box, and to explore uncharted territories of knowledge. So, what are the promising avenues for future research? For one, the advent of next-generation gravitational wave detectors could revolutionize our ability to detect wormholes, offering unprecedented sensitivity to the ripples in space-time they might cause. Furthermore, the exploration of wormholes in higher dimensional spacetimes and their potential connection to other exotic phenomena like cosmic strings or traversable wormhole networks presents a fertile ground for theoretical investigation. And of course, there's the philosophical dimension. The potential implications of wormholes for our understanding of time, causality, and even the concept of parallel universes are questions that straddle the border between science and philosophy. In essence, the future of wormhole research is as mysterious and exciting as the wormholes themselves. It's a multi-dimensional puzzle, a cosmic jigsaw that we're only just beginning to piece together. The quest to understand wormholes may well reshape our understanding of the universe and our place within it. Indeed, the very fabric of spacetime may be woven with threads of wormhole research. As we pull on these threads, who knows what new vistas of understanding we may unravel.